This will be your video lecture for chapters 4 and chapters 5. We're going to start off talking about symbolizing features. You can differentiate map objects in a lot of different ways by changing for example, shapes and sizes and thicknesses and any number of things, and you can infer different information simply by making these seemingly small changes. You can also use color to express a lot of information, whether it's to differentiate categories, to explain quantity, or how much things differ from one another. We do this by changing the different properties of the colors, like the hue, the saturation, and the value. We can also do a few things to make our efforts in this vein more understood, and that is by following accepted conventions and understanding the connotation of what we're doing, as well as taking into consideration things like color blindness. For example, if you're looking at temperature, if you look at the top left map of the US, obviously cool is blue, hot is red, and you can get some information from that. Other symbols like crosses and flags can be somewhat ubiquitous. In other words, it's hard to tell exactly what they mean. So if there is a particular symbol that is recognized universally or is important to a particular client or agency, then utilize those symbols that make sense. The same way with color blindness, certain combinations of certain colors might be difficult for some people to see, whereas in other instances when we make certain colors brighter, it works. And then obviously, if you got a map of land and water, don't make the water brown and the land blue. It just doesn't make sense. Rainbow ramps rarely work well for polygons. A rainbow ramp is when you have this range of colors that go from blue through greens and yellows and oranges into reds. Because in polygons it just tends to kind of look like you let a third grader loose with a box of crayons. Whereas in a continuous raster data set, it does look much more appropriate. Black and white maps, sometimes you design maps this way. And the main reason is it's cheaper to make, and some journals will charge you if you try to make a map of color. And so if maps are going to be faxed or Xeroxed, oftentimes it's better to make them in black and white. Ultimately, if people are going to use it as a black and white map, you should design it as a black and white map. How do you do that? Well, you got to pay a little bit of extra attention. Number one, you can't have more than 5 different color differentiations in your grayscale, because when you get more than that, it becomes really difficult to pick them up. Instead, what you're going to use is different patterns, and ultimately you may end up making more maps because you can't crowd as much information in, because you're limited in terms of the colors you can use. Here's an example of the same geologic map. One is designed to be printed in color, and the other is designed to be printed in black and white. And so it utilizes grays and patterns, or grayscales as well as patterns, to differentiate the different groups. So how are the different ways to map data? Well, there's lots of them. Single symbol, unique values, and quantity maps are all useful. Things like graduated colors and graduated symbols and dot density. And of course you can see on the right here we have nominal data, categorical, ordinal, and interval, and you can kind of see from the arrows what types of maps, symbols, work good for what types of data. Nominal data is basically names or unique identifiers. This is like objects such as parcels or tax IDs or something like that, states, counties, those sorts of things, where each individual feature has its own value and there's not duplication. And a lot of times this data is displayed simply as labels. And there's single symbols. In this example, we have a data layer that portrays the capitals of states, for example. And so what really matters isn't so much that the capital of West Virginia is Charleston, or that the capital of Virginia is Richmond. What matters is that every state capital on the map has a gold star, because the gold star is the single symbol that portrays that entity as in a state capital. Categorical data, that's where you have like a defined number of distinct categories, and this can be text or numeric, and there's lots of different ways that you can symbolize this. Below here there's 3 examples of different types of data and different ways that you can explain different classes within each type. Unique value maps utilize different symbols for each category or value. For example, going back to the previous map, we have different types of volcanoes, and they can be expressed by different symbols. Different roads can be expressed by, in this case, different thicknesses of the roads. And geologic units are expressed by different colors on the map, for example. Ordinal data. This is a type of categorical data where it ranks categories along an arbitrary scale, like low, medium, and high. Village, town, or city. A, B, C, D, F. Best places to live, like 1, 2, 3. And so you would literally have categories like this and then some explanation. Interval or ratio data. Interval data places values along a regular numeric scale. Think temperature, pH, elevation, something where you recognize and understand that the units are consistent and regular, and that there is a meaningful 0 point. That's how you can tell if it's ratio data, because you can't really have a negative value. If you have a meaningful 0, you can't have less than one you can't have less than none for population or rainfall, for example. Mapping numeric data. Interval and ratio data has to be divided into classes before you can map it. It's usually mapped with variations in symbol size, thickness, or U. Here we have point data expressed as different size point representations, roads, which are used in a wider line for the more lanes, and then we have precipitation that is classified out as a choropleth with different colors. And we'll also have class maps like this graduated color map or graduated symbol maps. Same basic premise. One, as values increase, the colors go from lighter to darker, or as values increase, the size of the stars increase. What colors to use? Turns out this is kind of important. You need a change in saturation or value to indicate larger quantities. In other words, if you stick within a red spectrum, you go from a very pale, light, whitish red up to a dark and brilliant red. In this case, sort of this rusty brown color. You can see that it goes from a very, very light tan, progressively getting darker as the value increases on the saturation. What you don't want to do is use multiple U's, because then it gets kind of looking like that third graders got into the Crayola box again. Normalizing classes can be important, and we do this for lots of different reasons. If the size of the sample impacts the measured value, then the data should be normalized. Let me say that again. If the size of the sample impacts the measured value, then the data should be normalized. So if you're looking at, for example, a number of farms in each state, the size of the area that you're sampling, i.e. states, is different. And so you would expect that would have an impact on the number of farms. So you can't just map the number of farms, because if you do, you get a map like the one on top. But when you recognize that that's the number of farms per square mile and you normalize it or otherwise standardize it based on the size of the state, you get a very different look. You can typically do this by dividing by some other field. Farms divided by area, homes divided by total housing are some good examples of that. Unclassed maps, sometimes you just use proportional symbols. Other times you just use dots and allow it to be a dot density. Now there's one drawback with the dot density. It makes it almost impossible in some instances to see information in the layers that are displayed behind your dot density, because in some cases the dot density overwhelms all the other data, and that the dots themselves basically black out everything. Then there's some of these more fancy things like chart maps. I personally don't particularly care for these. I find them to be highly difficult to comprehend in totality. You can find individual areas and look at the graphs and make sense of it, but as a whole, it just looks like a stack of cookies across a map. Same way with the little pie charts and the bar graphs. I just don't personally care for them. I want to talk to you a little bit about MAP, Modifiable Area Unit Problem. Modifiable Areal Unit Problem. It's an arbitrary aggregation unit issue, like states. or counties and how it influences values. What it means is you have a modifiable real unit problem when an artificial boundary potentially changes the outcome of the value in question. For example, where you draw state lines may impact the values that you see for a particular state. There's an old joke about the panhandle of Oklahoma. Now, if you chopped it off and gave it to Texas, it would raise the IQ of both states. That indicates that intelligence across Texas and Oklahoma is not based solely upon the state boundaries, but rather more of a geographical influence. Now, obviously, that's not the case, but nonetheless, what the joke illustrates is by changing a border, you change the value of a larger area. And the reason is because when you modify the area, it changes the value. That is a classic example of a modifiable real unit problem. How do you minimize it? Well, the first thing you do is try to normalize your data, in this case farms by area of the state. And that makes a tremendous difference in the output and what it looks like. Here's another example where we look at housing, and you can look at vacancies by number of housing units as opposed to just a strict number of vacancies, where in some instances it makes it look like California and Texas and Florida have the most vacancies. But in reality, California has more of a housing shortage because while it has a lot of vacancies, it has many more units, and so the percent vacant is quite low. Whereas other states like West Virginia have relatively few numbers of vacancies, there's also not nearly as many houses, and so our vacancy rate is actually among the highest. So you can divide by the total of a column, percentages of Congress controlled by each state, those sorts of things, or other ways of normalizing. There's also this issue of a visual impact of the modifiable real unit problem. Large polygons tend to dominate the map, and they're more prominent and they attract greater attention, and there's just not a lot you can do about that. What you can do is use things like graduated symbols or dot density maps to highlight the information, not so much the underlying data. And so when we look at numbers of farms, in this case, the choropleth map makes it look like, or at least your eyes are drawn to, the darker areas, and things like states like Texas and California sort of draw out at you, even if maybe they're not that much more important. Whereas when you use the dot densities, those other things don't seem to matter as much. What do we do with rasters? We love rasters. Rasters are cool. Okay, raster types. We got two: discrete and continuous. Discrete represent objects that have starting and stopping points, like lines and polygons, and it takes on relatively few values. And generally, adjacent values often have the same value until you get a point of change, and then the value changes to the new value, and it remains that until it goes to the next point of change. Much like the picture on the top right, where each cell in the raster is a 10 until you get to the ones that are 14s or 9s, and then you move on around your raster, etc., etc. Where rasters really find their role is with the continuous data, where you have thousands or even millions of potential values, and very rarely do adjacent cells have the exact same value. In fact, sometimes they change dramatically from cell to cell, and we can look at that across a large geographic area and see the change in the variable in question across the space. We can also have thematic rasters and image rasters. Thematic rasters can contain quantities that represent map data such as land use or rainfall. And they can be either continuous or discrete. And then there's image rasters or pictures. These are basically satellite or aerial photos, and they generally represent only two things: the brightness or some sort of a usual continuous color, because the only thing that really is stored in that is the pixel value for the color of that individual pixel, and then collectively it shows up as an image, but it doesn't actually infer a specific value other than what the color is in each pixel. Raster pyramids are important. They're used to speed up the display of rasters. As you know, rasters are a very inefficient way of storing data because it's, well, just a bunch of tiny cells, and you have to have information for each one, where polygons can often be really large areas that only have a single value that's representing it, and it would take hundreds if not thousands of raster cells to make up the same location. What pyramids are is a successive lower resolution copy. Now once you build them, it takes some time to build them, but once they're done, you can use them repetitively. Now it does increase the volume or the size of the data file by about 50% because it makes multiple files. In this example here, you see that you start out at 1 to 12,500, then it creates another version of that that's at 1 to 25,000, then one at 1 to 50,000. And the idea is that the coarser versions, when you're zoomed out, allow you to move around the raster without being forced to re-render all that data for the new location. Because when you have a really detailed raster and you move your field of view, basically as you're moving it, it has to recalculate what it has to display and do that for every pixel. If you have pyramids, it does it for the lower resolution copies based on how zoomed in or zoomed out you are. We can display thematic rasters a lot of different ways. We can look at categorical or ordinal data using things like unique values and discrete colors, intervals and ratio data. Oftentimes we just simply classify those or stretch them. When we stretch them, we use a particular color ramp where we go from our low value to our high value and space the values out accordingly in between. Slicing is the first thing that you have to do when you do a lot of this stuff. Slicing basically bends your raster in values from 0 to 255. So let me just go back at what this does. It looks at your minimum and your maximum value. Okay? It sees how many values you have. It divides that number by 255, and then it starts at one end going towards the other, and it adds in those values. So for example, if you had, we'll just use 255. If you had 255 was the range from your minimum to your maximum, the very lowest value would be a 0. The next one would be a 1. The one after that would be a 2. All the way up till you got to your highest value, and it would become a 255. It will then take those colors, those 255 colors, and match them up to the 256 colors, which is from 0 to 255, in this ribbon or rainbow of color that you see underneath the figure. And then it would take those data and generate an image, if you will, a color image on the right, like you see. Now, sometimes what we find out is that there's a whole lot of data points. There's not a whole lot. There is many of these color spaces that we waste for very few data points. And so if you look at the distribution of data in the graph, particularly off to the right, you'll see that there's a lot of data. There's just not very many. Now, when I look at many, think of 0 at the bottom of the graph and a really large number at the top. And so the further up the purple goes, the more occurrences there are of that number. And so when you're looking on the right side of the second black line, what you're seeing is there's a lot of data out there in terms of number, like from say 1,000 to 5,000 or something, but there's not a lot of each of those. When we stretch an image, we basically chop off the ends and add them all to the next value in. And basically it enhances display by taking the part of the distribution of your data where the majority of your data exists and spreading it out so you differentiate the more important things. And what does that do? Well, if you look at the images here to the right, the original image looks like the one on the left, and then after you apply something like a standard deviation stretch, which goes in one standard deviation from each end and removes or groups that data together with your lowest points as a single point and then divides the rest out, effectively stretching it out, you get the figure on the right. And some of you might say there's not much difference there, but the difference is in the degree of detail that you see in the middle data, which is where most of the data is, which is where a lot of the most important stuff happens. And now you pick up additional detail because fewer values are binned together. Image display, single band versus multi-band composites. Images represent brightnesses from 0 to 255, or a DN number, a digital number. In a 3-band composite image, you have a red, blue, and a green, and within each color you have a digital number that represents how light or dark it is in that particular color. When you combine them, you get a real color image. So again, just a quick once over. Image usually contains 0 to 255 range of values, but the whole value is not always utilized. An example, if we have an image, it might look like the one there in the middle where there's no stretch applied. If we go in and do a stretch, where we use something like standard deviations and we cut the tails off of that distribution and bin all those really low numbers and all those really high numbers together and stretch out the ones in the middle, the exact same image that you see in the middle looks almost entirely black becomes the image on the right, which actually indicates a lot more detail, makes it a lot more useful. So what are the effects? No stretch. If you use a minimum maximum stretch or standard deviation, you can see how each of these allow different degrees and different levels of detail to become apparent. Red, green, blue composites, like I mentioned earlier. You take multi-band images, you have a digital number, a DN number, which is basically how bright or dark the color is in each of those spectrums, and so you'll get those 3 images look like the 3 on the left. When you combine them, you get the one on the right. We talk about Landsat satellites. These are some of the earlier but yet very prolific satellite resources that we have to collect remotely the kind of data that we often want to use in GIS. And it collects different bands, and they're numbered, and each one is unique for different reasons and the wavelengths that they're picking up or measuring. In this example here, if you want to have a true color image, which is a red, green, and a blue, you use bands 3, 2, 1. Band 3 is red, band 2 is green, band 1 is blue. If you want a false color infrared, use 4, 3, and 1. There's other combinations like 7, 4, 1 that are designed to identify certain things based on the combinations of bands and how the bands are assigned. We also do things called an indexed color raster. This is basically more like we have specific colors, and the colors in the raster respond or relate to a particular thing, and sometimes they're very detailed. There's not many classes. In other instances, it's really problematic. 0 is another common value, but 0 is not the same as no data. No data can be very useful. So when you have a raster and you're classifying it, sometimes your raster doesn't line up exactly with other things, and there's certain cells where once it's been rectified or georeferenced, it doesn't have a value in a particular cell, and so you can do a couple of things. You can assign it a value of 0, or you can call it no data. If you assign it a value of 0, it has a value of 0. If you call it no data, it's like it doesn't exist. And it turns out later in the semester, when we're learning some other things, there's ways that you can utilize this function, this no data function, particularly when you want to convert between raster and vector data. Transparency. One of the things that we can do a lot of in GIS is we can take, for example, something like a hillshade, which indicates creates a certain sun angle, and then based on that, and you take a digital elevation model, it makes one side of the hill dark and one side light. You can then take something like, for example, a geology layer, and take that layer and apply it over top of the hillshade. Then by adjusting the transparency of the geology, you can see the hillshade through it, and a lot of times it allows you to understand how they actually come up with some of these other data layers. Okay, let me record that one again. How do we classify numeric data? Well, there's several ways. Okay, here are the primary means of classifying data. These are the 6 that we apply to both vector and raster. There are other ones available. The choices are impact to map appearance and validity. And the best method depends on the data and what you're trying to, what your objective is. So we have the Jinx, natural breaks, equal interval, defined interval, quantile, geometric interval, and standard deviations. And these maps are all the exact same data set with different classification schemes, and you can see how it makes a dramatic difference in the way the data looks. Data also has a distribution typically, and they're not all normal. Some tend to be skewed, some are very uniform, some are bimodal. Jenks natural breaks is probably the most common, and it's generally the default. It's the one we most often use. It exploits natural gaps in the data. It's good for unevenly distributed or skewed data, and it works well for most data sets. How does the Jenks natural breaks method work? Well, you tell it how many classes you want, and it looks to group the data together so that the average standard deviation based on the standard deviations of each class are as low as possible. So it divides the data up into, say, we're looking at 3 classes. Within each class it would measure the standard deviation, and then it would average the standard deviation of all 3 classes and get a number. It would then shift those breakpoints around to determine where data goes, whether it's in the first class, the second class, or the third class. Do the same process again. And it will continue to do this until it finds the lowest average standard deviation, which means that within each group the data is more like itself, as much like itself as it can possibly be. Equal interval was just that. Equal interval, think of tax brackets or income brackets in census data, or age going in like lots of 10, so like 10, 20, 30, 40, 50, 60 years old. Those would all be equal interval. Defined interval is a little different. Maybe you have particular categories that you're interested in, so you set those categories up. Quantiles are also commonly used. The clever thing about quantiles is the value within each of the quantiles is very different. The range from low to high within each quantile is very different. The thing that is the same is the number of data points in each quantile. So if you have 3 quantiles and you have 30 data points, the first 10 is the first quantile, the second 10 are the second quantile, and the last 10 are the third quantile, going from low to high. That's basically how quantiles work. And so it just evenly groups your data up based on number or count, and then whatever that value of that cluster or group is what it is. Geometric interval basically uses more of a math function to determine that. Works well with skewed data, and really the take-home message here is if you look to the breakdown on the right, you'll see that you don't go very far and you have your first break, but you go 2 or 3 times as far to get to the second one, and then 2 or 3 times that distance to get to the third break, and then 2 or 3 times that distance to get to the fourth break, etc., etc. And so the distance between the classes continues to grow. Standard deviation is also commonly used, and this you use units like a half a standard deviation, and it assumes that your data is normally distributed. Okay, so what do we know about mapping GIS data? I want to talk about dynamic labels. You're wondering what a dynamic label is. One of the layer properties that you can turn on and off for entire layers is labels. And you can redraw each time the map view changes. You can use auto placement to ensure that things don't overlap, and you may change between screens and printing. And so basically it follows a set of rules that you give it in terms of where to place labels, and it just automatically updates it every time you move. You can go in and determine where these things are. Here are some of the controls, like label placement, and what the options that you'll have. And you can tell it where to place it in terms of the point, how it goes. There's lots of opportunities there to adjust that. All these you will learn as you do the tutorials for these chapters. Again, where do you place the labels? Lots of options. Same way with lines. Whether you have them on the line, above the line, or following the line, there's lots of ways that you can do it. Then there's scale. Turns out this is kind of important. Notice the little box to the right where it says don't show labels when zoomed, and it says out beyond or in beyond. You can literally set thresholds, so if you zoom in close enough, things kick on or kick off. And the reason you do that is because if you leave labels on sometimes at certain extents, It makes it impossible to see the data because the labels just become a giant mess, laying on one on top of each other until you can't see anything. It's your labeling toolbar. How do we symbolize featured? Again, we've already talked about the different things that you can do earlier, different styles of things that you can use. You can go in and edit the individual symbols, like for example if you're doing an airport and you know that departing planes leave in a certain direction and landing planes come in from another side, you literally could point your little airplane in the direction that you want, whether to symbolize something landing or taking off. As far as our maps, we have single symbols, unique values, and quantity maps, where we use things like graduated colors or symbols or dot densities, as well as the other techniques. Within each of these, we typically have more things that we can adjust and choose and change. A little bit better breakdown of the different types of data and the symbols that we typically associate with each of those in terms of how we explain or express those values. Single symbol maps are pretty straightforward. Everything has the same symbol. You just change the details about the colors or the outlines, etc. When you look at unique values, you might have a whole range of things depending on what your value is you're looking at. Or maybe it's a numeric variable like a population number, and you're going to classify it down into groups. Maybe it's something you normalize. There's functions there within the symbology to add in your layer that you're going to normalize your data with. You can select things that you want for graduated symbols, determine the number of classes, determine what the maximum size and the minimum size you want on your symbols to be so that it divides them up in between. Or if you're talking something like lines instead of symbols, you can control that as well. You can go in and apply some of those classification techniques to classify your data. When you open up the classification window, you can tell it the method, the number of classes. If there's things you want to exclude, you can manually go down here and move these breaks around if you like. Just want to point out, if you manually change a break, it's no longer Jenks natural breaks. It becomes the user-defined ones. Excluding data, there's different ways to do that. You can run some little scripts there to pull out data sets. Symbolizing rasters is a little different. The unique values come up and typically follow a certain set. You can also look at discrete colors, or you can have one that's been classified or even stretched, or a multi-band satellite image. And it can be combined in something that you're not typically used to. Not your red, green, or blue. It could be one of the unique combinations. So the next thing we're going to talk about a little bit is Chapter 5, Presenting Data. And this covers just more of the basic principles of map design. This whole process of making maps is an iterative process. In other words, it repeats upon itself. You make corrections and then you redo. You make corrections and you redo. And you go through the process until there's no corrections left to make. In this diagram, we start off with some data that we select based on our objective. We arrange it based on our objective. We symbolize it based on our objective. We review the map that we've made and see how well it suits our objective. And we edit it and make whatever changes we need. And then we either accept the map or we go back and select more data to add to it to make it better. All the while, as we go from selecting and arranging and symbolizing and reviewing and editing our map, we're always cognizant of our objective, because the goal of any map is to get across the point that you're trying to make. Take your data and present it in a way where it's not just presenting data, but you're converting data into knowledge. In order to do that, you have to be constantly aware of the objective behind what you're trying to map. So what are the map objectives? The first thing is to look at the design step, and there's 4 questions. What's the purpose? Who's the audience? What's the medium? How will it be viewed? What does that mean? Purpose. What are we trying to do? Audience. Who are we showing this to? Medium. Is it printed? Is it displayed? Is it in black and white? These are the questions you need to ask. Under what conditions will it be viewed? Will it be held on a piece of paper? Will it be printed out on a 40-inch poster? Will it be shown on an overhead projector? All these things make a huge difference. Maps serve a lot of purposes. They can be used for locating things, navigating, compiling, convincing, comparing, analyzing, and any number of other things. Think about your audience. Who are they? What's their level of knowledge and understanding of what you're talking about? Do they have any special requirements like color blindness? Do they need large print because they have poor eyesight? Know your audience. That way you can make a map that well suits their needs. The medium: paper, electronic, computer, projector, mobile devices, or tablets. This is actually one that's really growing a lot. Whether you're designing websites or maps, a lot of times one of the things they ask for is to make these elements that are mobile device accessible. In other words, they're optimized to perform on handheld devices like iPhones and tablets, as opposed to just on traditional websites, or maps that will be viewed in that fashion, as opposed to printed out on a plotter, used in a poster, or seen on a computer monitor. When you're talking about the medium, paper maps are static and unchanging. Web maps tend to be interactive. Think about the fixed sizing and scales that you might have, the resolution and the complexity that you can display before it becomes too much and then draws away from the intent of your data. Understand that it could be viewers could be committed to it, and that it might serve multiple purposes, whereas in web maps, oftentimes you got poor light or sunlight and mobile devices. You have viewers that have a very short attention span, and you're competing for their attention. And so in those scenarios, you probably want to make a map that does just a single thing and just try to do it really, really well. Selecting, we already talked about that. Select the data layers. A good map tells a story, so you need to know who your lead players are, what the supporting roles are. Do some layers distract from your story, or do they obscure it? And so, for example, in the map above, the beautiful background map just makes it look too busy. Whereas if you turn down the intensity and make that more of a faded look to it, it doesn't interfere with the data nearly as much. Should you kick some data out? Privacy issues are always a big one. You should be very cautious when publishing the owner's names of parcels, for example. Then there's things like sensitive information. You don't want to post information on where you find fossils or archaeological sites. There can be issues of poaching, where people will come in and try to dig up those materials and sell them for their own profit. Or maybe you have pipelines or climate stations, and the big thing is you don't want some yahoo going in there and chaining themselves to a dozer, or tearing down a weather monitor station, or painting "I love Sue" on the side of all the equipment. And so there's some things you just don't want to put out there. Unintended economic consequences. If, for example, you show where fault lines are, or where you have areas that have a higher likelihood of having radon gas in basements or something, or have poor water quality, this could drive down the price of real estate in those areas. So you got to be careful of those kind of things. Within layers, you can select a lot of data individually, and then you can group things together and generalize it. You can adapt large-scale and small-scale maps to your particular needs. You can use queries to select subsets. In this example, we have all these earthquake data, but if you're only really interested in the big ones, it's best to pull out the big ones and not worry about the small ones. Just some examples of some cartographic generalizations. We use a tool like refine. We just change it a little bit, simplifying. Aggregation, where we bring together these disparaging parts into a single thing. Collapsing, reclassifying, typifying, displacing, and exaggerating. Next thing we're going to talk about is how you're selecting a projection. In the last chapter 3, we talked about how important projections were, and how each projection often brought some degree of distortion to your data. Well, when you look at a map, you have to determine what coordinate system it's in, and think about what you want it to be in for what you're trying to do, and then select a projection that works for you. If you're looking for a map that's aesthetically pleasing, something in the GCS is just not going to work. You're always going to want to use something that's projected to give it that more eye-appealing look that we're accustomed to. Three basic types of projections: cylindrical, conic, and azimuthal. Every projection choice may affect the story of your map. Mercator maps make the northern hemisphere look more important. The top one is a Mercator map, and I want you to notice the size of Iceland. If you're not sure where Iceland is, it's that giant chunk of land that's about the size of the United States, poking down from the Arctic between North America and Europe. Now, in reality, if you go to the bottom map, you'll see something that really truly represents more what the size is, and it's nowhere near as big as it appears in the top map. In fact, in the top it's nearly the size of Africa, when in reality it's only about 1/17 the size of the continent of Africa. So what's the story? Iceland, the big purple country there, it's not that big. Gradical grids. When you have a conic projection, north is not a single direction, it is a progression of directions. So north is not pointing straight up on a map that is in a conic projection. You have to add on these grid lines that are based off of a gradical, because that sort of tells you that, off to the right the north points to the left, and off to the left the north points a little bit to the right. There are other types of grids that we put on maps. Sometimes we just measure things off of grids, like UTM maps, to show where the coordinates are. Other times we use a reference grid because we might want to tell somebody to go to D4. So you go on the D and the 4 and you find where those two sections meet up. Think of playing Battleship, where you call out your shots: C2, F8, and then somebody yells out, "You sank my battleship." Arranging your data. Visual hierarchy is important in order for a reader to perceive different objects in a design. You have to make sure that the important stuff is positioned such that it draws your attention, and that the less important things are not positioned to where they distract from that. A good map establishes a clear pathway that highlights the importance of these aspects. So we're going to look at some maps and talk about them briefly. Here we got a nice map. It's got a little insert map. It's got a nice big legend. It shows a lot of things going on there. There's a lot of information. We got the known number of eruptions. We got the population of the counties. We know roughly where this is at in the big picture of the United States. We've got a tiny little error bar down there. We've got some data referencing. We've got a scale bar. Yeah, there's a lot going on there, but it doesn't do a bad job of explaining that there's certain volcanoes that are near certain counties that have a fair amount of people that have erupted many times. So what is it about the map? What's the first thing you noticed? How did your eyes move around the map? What was the perceived path? When you look at that last map, you should have been drawn to certain things like those big reddish brown triangles, and once you figured out where they were, you should have started to look to see what they were, and then you should have noticed the colors underneath and said, okay, what do these colors mean? Look that up and make sense of that. And then as you're starting to process the information, you want to know whereabouts we're talking about in a larger sense. You can look at the smaller insert map and see that we're talking about 2 states in the Pacific Northwest. So when you establish a visual hierarchy, there's certain things that you want to do. The visual center is something. Rule of thirds, balance, alignment, negative space, neat lines, symbolization, colors, contrast, size, thickness, foreground, and background. We'll talk a little more about these. Visual center is not the center. It's actually just a little bit higher than the true center. And so you want to make the most important things be slightly above the center line of your map. The rule of thirds says basically you don't ever want to place anything in the direct center of the map. Imagine drawing your map up in thirds, and where 2 sections meet is locations where you want to place things, not dead center in the middle. In the example on the top, you have this group of people in the middle of the map. It's fine for whatever you're doing, but the picture on the bottom, where they're down there more into the lower left corner, it just looks right. Alignment, basically you want to use columns and you want to align edges so things line up and look neat and spaces are even and well thought out. Negative space is the utilization of white space or unused turf, if you will, on your map. You need to balance it out so you don't crowd things. Don't leave too much. Don't try to fill up every inch either. Use it as a design element. It's a subtle way to group things together to make them look better. And so the map on top is not a very good map, whereas the map on the bottom is a very good map. So some examples of how you can place things to balance out your elements to make your map look better. Okay, back to the next one, symbolizing data. What stands out, how is it achieved? Think about the colors, the contrast, foreground, background, size, thickness, symbol, font, spacing, grouping. What are you doing with your data to make it appear more or less important, and are you conveying the message that you intend with the data that you're showing? Don't just use patterns that make sense, use techniques that make sense. You can put things together like different patterns and colors, but make sure what you're doing works and then it doesn't create a busy map that makes it difficult to read. So here we've got two maps. Which one gives us the best degree of clear visual hierarchy, and how do they do it? Well, the one on the top is not very good because the blue for the ocean is really dark and it draws your attention and it makes it really hard to tell what's going on. Where the one on the bottom, the background, the ocean, is lighter and allows you to then notice that we're probably more interested in the color of the individual countries, and then we can see what they are. Base maps are important, but they're not always necessary. Base maps can be useful so that you can see the context of where things are located, but that is their main purpose. Alright, next we're going to talk about reviewing and editing your maps. You want to check the balance and the visual hierarchy. You want to print it out to see if the colors work. You want to check spelling and grammar and the fine details. And did you remember to add your data sources? These are all important components in the reviewing of your draft maps. Pay attention to the little details. Here's an example of two legends. The one on the left is what we like to call bad, and the one on the right is what we like to call good. Notice how the text is crowded up against a neat line that outlines the box. The data that we're looking at has the shape file name cities.shp, which is fine for when you're playing around with it, but when you want to make the map, you need to make sure people understand that this is US cities 1990 population. So instead of cities.shp pop 1990, do away with the abbreviations and change the text and the legend to reflect what you want, and pull that stuff away from a neat line around the outside. And then lastly, look at your basic formatting of your numerical values, adding the commas in at the right places and that kind of stuff to make it more user friendly, easier to read, and less confusing. So you'll get a map somewhat like this when you're done, and then you get an opportunity to look at it, and so this is a chance for you to review it. As you're thinking about what you see here, notice that you got Alaska up there in the corner, which is just really awkward because the particular projection makes it look small. In reality, it's half the size of the US pretty much. It's also not doing anything for this map other than making it crowded in the way. You have this title, household size, which is kind of vague. It's got this huge drop shadow, which is just a big waste of space. The legend doesn't look horrible, except it says legend, and you don't have to say that. We all kind of know it's a legend. But when you look down to your county's data, you got AV HHSZ. I understand that that's household size, but that's because I've taught this class several times. So you should make that more clear. North arrow is fine. Don't like the location. Scale bar is fine. Not sure why we haven't, what the purpose is in this case if we're not measuring something. Choose a landscape layout, blah blah blah. There's a little text box there. Notice that it's been used with a justify font or justify spacing, which throws out these unusual size spaces, which looks bad. Another map you can look at similar kind of things. You see the household size, the data at the bottom, nice label, neat lines work, much better design. External review is also very important. It's very helpful to have other people review what you've done to see your map. People who are one of a few things. You want people to look at your map who are similar to the people who are going to be looking at your map. So if you know what your intended audience is, find people similar to them and have them review your data and your maps and make sure that they They understand what you're trying to show, and if they don't work your map again. You can also use people in your field, so if you're making maps about a particular topic, you can have other professionals in the field that makes those sort of maps review it, give you their concepts. If you can find one, a nice graphic designer is also very useful in terms of they understand how these elements go together to enforce or detract what you're trying to, whatever your message is for your map. And so a graphic designer is also a good person to review. 3-second test. I want you to look at the map on the next slide for 4 or 5 seconds, then we're going to talk about it. We're not going to do that. We're just going to look at it and go on to the next one. You can think about it if you want. Got a nice map there. What do you tell from it? What's wrong with it? What's not wrong with it? There's always some problems. You're done, maybe. Okay, yeah, basically what we're looking at here is once you get to a certain point, you're going to go back and see, now you've done this, do we have what we need? Do we add more to it, or do we need to work around the wheel one more time? So let's look a little more about Chapter 5. Page layouts and map scales. Here's an example of a layout. This is kind of busy, has a lot going on. I don't know whether I would consider this a very good map. Layout toolbar. You can see all the different tools and what they do. When you're in the layout view, it allows you to look at what the map product will look like as opposed to just looking at your data. Basic steps to layout: plan the map, setting up the map, adding the legend, the scale bar, the titles, the text, the objects, the neat lines, the graphics, and printing off your map. Visioning your map page: think about how things are going to go on there, what you're going to put in there, what grids or aligning features you need to make things work, how you want to position stuff, those kind of things. Once you figure it out, you can pretty much roll with it. You can use predetermined map templates. You can set up page sizes for things that you want. If you know you're going to make a map that's 40 inches tall and 60 inches wide, just go ahead and make a 40 by 60 map document and put everything in there, and it will be the size it looks. You can switch to other templates after things have been created, but oftentimes it makes things not fit the best. You can assign frames. You can print, portrait, landscape. You can have quite a lot of control over some of that aspects of what things look like. Composing frames, dragging things around, that kind of stuff is pretty easy. Scaling your maps, automatic, fixed extent, etc. You can, and you need to understand your unit terminology. There were several questions on your exam this week about map units, display units, and page units, and storage units. You need to understand what each of these things are and commit it to memory. That map units are determined by the data frame. The display units are what you set to see. The page units are what show up on your map. And then ultimately, if you have storage units, that's the units that go along with the data as it exists independent of your map document. And so here are some of the boxes that we commonly associate with these units and where you find them and what they mean. How do you set them? Labeling and annotation. Labeling options. Dynamic was included in Chapter 2. Graphic text is another one. And then there's annotation, which is usually created from dynamic labels. Dynamic labels. You can go into your labels, turn on your label features, set things up the way you want. Graphic text, you literally just go in and add it. It's like adding a floating text box, and you can put them where you want them to go. You can add multi-line labels as well. And there's a label tool. You have to use it when you're in the data view. And there's annotation. Annotation are created from dynamic labels, and then they're edited individually. Basic concept of annotation is you turn on your labels, you set them up. You then convert them from a dynamic label to an annotation. This disassociates them from the data that you had previously, and so now instead of being a label for each polygon, it's simply free-floating text that is associated with that spatial area of that polygon. It then allows you to go in, to move them around, change their location, change their angles, change their font, change everything about them independently, and they're no longer linked or synced together. This gives you a lot of flexibility in how you edit, position, and otherwise display labels. Default scaling, you can see how it shows up and things get kind of jammed together. When you scroll in, they're not so scattered together. They're not so jammed together. They're more scattered out. But that uses the same sort of baseline 10-point font. Reference scale is the scale the symbols appear when they're assigned. Creating annotations is not that difficult. You can get in here, you can see how to do it. Use the convert labels to annotation feature and work through the tool. You can get something called overflow annotation, and so if you have too many labels, it won't always put them all on the map, and you can bounce them over into an overflow container. Basically, if there's not enough room for all of them, it just puts some of them off to the side where they don't show up on the map, and then you can go in if you want one of them and grab them and bring them out and place it where you want, or take the ones that are on the map and put them in the can with the overflow. And then you can group them together as well and do some other cool stuff. These are the kind of things that you'd have to make a lot of maps for this to become something you would use on a regular basis, but if you get a position professionally to do that, these tools will save you a lot of time, as well as doing features. Adding map elements is the next topic we're going to look at. Adding a legend, simply go up to Insert, hit your Legend tool, and it opens a legend wizard. The wizard is not from Oz, nor is it from Harry Potter or Lord of the Rings. It's just simply a little graphic user interface, a GUI, that allows you to select the variables that you want from all your map layers, and they're going to go into your legend. You can tell it how many columns you want, and other sorts of things. You can give it a title, change the color of the font, the spacing, the justification, and all that kind of stuff before you proceed. You then have some other elements that you can control, like borders and backgrounds and drop shadows and all this sorts of stuff. And then once you have everything set up, it will then generate a legend. Again, lots of controls over elements. And once it's done, it's done. You can always go back and right click on it and open up the properties and modify it if it's not what you want. But once it's set up and finished, you'll have a nice legend there that displays the information that you need to understand your map. Here are some different styles. Changing the legend, the different things you can change, what they are and how they work. There's some additional tools for how you manage some of this stuff as well. Scale bars, again, go to the Insert menu, add it, up comes a GUI, find the one you want, adjust the properties, tell it how many divisions or subdivisions or ranges or units, whatever it is you want, and then it puts it in. In general, how wide should a scale bar be? Somewhere between 1/4 and 1/3 of the way across your map, or your area on the map. So not the whole page, but in this example, like you have a map there of the US, the continental US, you would want to kind of run anywhere from 1/4 to 1/3 of the way across. Again, divisions, the widths, and the number of them, all these are things you can adjust when you're creating a scale bar. North arrow, man, there's a bunch of north arrows. Just remember, if you're in a conic projection, you can't add a north arrow because it would be wrong. You need to add gradical lines. There we go. Open the grid and gradical wizards, for conic projections that need north and south identified. And this takes you through the whole process of adding either the gradicals or the grid lines, depending on what you want. Text and titles, basically just inputs text box that you can then use to add additional information, whatever it might be. You can also insert pictures in your maps. This is sometimes a pretty common technique. Sometimes it just destroys your really good map with a picture and makes it too busy. Other times it adds quite a lot of meaning and context to what you're trying to say. Neat lines, also known as borders, are important. This not only contains what borders you select in the backgrounds, but whether you use drop shadows and all that kind of stuff, and how they're placed and what they're placed and where they're placed. You also have a graphics toolbar that shows all kinds of different tools, allows you to draw shapes, freehand things, add text and font, and any number of stuff. So time to review your maps and get ready for printing. If you're going to print a map, go to the setup, make sure you know where you're printing it from. Look at how it looks. Adjust things like your paper sizes, your sources, your orientations, your page width and height, if you need be, to make things fit neatly on the page of the paper or the printer or whatever it is you're printing it with. You can also, instead of printing it like that, you can export it. This allows you to take your map and save it as basically a PDF or a JPEG, which you can then share and swap around or export or email to other people. This is how, when you make maps for graded homework assignments, you should, when the map is finished, export the map as a PDF, and then take that PDF and upload it as a file response.